All right, let's talk about a question that's at the heart of pretty much all machine learning. You go through all the work to train a model to make a prediction, but how do you actually know if it's any good? Today, we're going to break down the key ways you can measure just how good your guess really is.
So let's just dive right in with an example. Imagine you built a model to predict house prices. It looks at the data and spits out a number, say $350,000. But the house actually sold for $370,000. Okay, so you were off. But by how much, really? And is that even a big deal? To figure that out, we need a consistent way to measure how close our guesses are to the real answer, not just for one house, but for all of them.
This quote really hits the nail on the head. The choice of a loss is everything. Now, loss sounds a bit technical, but all it really means is how do we penalize our model for being wrong? It's a way of scoring the error, and picking the right scoring system is absolutely crucial.
Okay, so where do we start? Well, let's look at the most foundational way to measure error. And what's really kind of cool is that the logic behind it actually comes from a totally different part of machine learning, clustering. Yeah, this is the key idea right here. In an algorithm like k-means, the whole game is to minimize the squared distance between a data point and its cluster's center. And that little trick, squaring the error, is a powerhouse concept. It does two really important things. One, it makes all the errors positive. And two, it punishes the big mistakes way more than the small ones. That makes it much easier for the algorithm to find the best possible answer.
So we can steal that exact same logic for our house price problem. For every single prediction, we figure out the error, the difference between what we guessed and the real price. Then we square it. So an error of 20 becomes 400, but an error of 10 is only 100. See? The big mistakes get blown up. And then we just take the average of all those squared errors. That's it. That's mean squared error, or MSE.
Now, MSE is fantastic. It's the workhorse for training models. But it has this one kind of nagging problem when you try to explain your model's performance to an actual human. The units are just, well, they're weird. So let's make a little tweak to make our metric way more intuitive. And here's the problem. If you're predicting prices in dollars, your MSE isn't in dollars, it's in dollars squared. I mean, seriously, try to go to your boss and say, hey, our model's average error is $625 million squared. It just doesn't compute in our brains. It doesn't give you a feel for how far off the predictions are in the real world. And the solution is so simple, it's brilliant. We just take the square root of the MSE. That gives us the root mean squared error, or RMSE. By taking the square root, we basically undo the squaring we did before. And bam! Our error is back in the original units. So instead of dollars squared, our error is just dollars. An RMSE of $25,000? Now that's a number we can actually understand. Okay, this is a huge step. Our error is in units that make sense. But we're still missing one absolutely critical piece of the puzzle: context. How do we know if our error is good or just plain bad? I mean, think about it. An average error of 25 grand sounds like a lot of money, right? But what if you're predicting the price of mansions in Beverly Hills where everything costs tens of millions? In that context, being off by 25K might be an amazing prediction. But if you're predicting little studio apartments that cost 150K, then a 25K error is, well, it's terrible. It all depends on the baseline.
So to get that baseline, let's pit our model against the simplest, laziest, most naive model we can possibly imagine. This naive model doesn't care about square footage or a location or anything. For every single house, it just guesses the average price of all the houses. It's a pretty low bar to clear, but hey, if our fancy model can't even beat that, we've got bigger problems.
And what's really interesting is that the error of this lazy, average guessing model already has a name in statistics. It's called variance. All variance really measures is how spread out the actual house prices are from their own average. So in a way, the variance tells us the total amount of error we're starting with before our model even tries to make a prediction. And this comparison is what lets us build what is maybe the most useful metric of all, R squared. Conceptually, it's asking a really simple question. Out of all the total error that exists in the data, how much of it did our model manage to explain away? It literally tells you the percentage of the spread in prices that our model was able to capture. The best part is that interpreting R squared is so straightforward. An R squared of 1, that's a perfect model. It explains 100% of everything. an R-squared of 0. That means your model is no better than just guessing the average every time. And yeah, you can get a negative R-squared. That means your model is so bad it's actually worse than just guessing the average. So obviously, a model with an R-squared of 0.85 is way, way better than one with 0.4.
All right, let's put it all together. Enough theory. Let's see how this works in the real world when you actually have to pick which model is the best one to use. It's time for a model showdown. So here we go. We've got two contenders, Model A and Model B. First, let's look at the RMSE. Model B has a lower number, 22,000 versus 30,000. That means, on average, its guesses are closer to the real price. So, point for Model B. Now, R-squared. Model B has a higher score here too, 0.86 versus 0.75. That means it explains more of what's going on in the data.
And this chart just makes it crystal clear. That naive baseline, just guessing the average, it's got a massive error of $60,000. Ouch. Model A comes in and cuts that error in half, which is a huge improvement. But then look at Model B. It's the clear champion, bringing that error down even more, to just 22,000.
So yeah, the choice here is a no-brainer. Model B is better on every front. It has a lower typical error, and it captures a whopping 86% of the patterns that drive house prices. And this is why these metrics are so important. They're not just numbers on a screen, they give us a clear, quantifiable way to prove which model is objectively better and deserves to be used.
But let's end with one last thought, a little something to chew on. Everything we talked about, MSE, RMSE, R-squared, it's all built on the idea of squaring the error. And that's great until it's not, because it makes these metrics really sensitive to outliers. One single crazy wrong prediction gets squared, and it can blow up your whole score, making your model look worse than it really is. So what if you wanted a metric that was a bit tougher, one that wasn't so easily pushed around by a few bad guesses? Well, that is a fantastic question for another explainer.